Yep.
Hi, my name is Peter Riemersma, and I'm currently in the Geology department at Grand Valley State University. And we're here at Almond Park looking at Sand Creek. And we had a lot of rainfall, so Sand Creek has a pretty high water level, pretty high discharge. And my students at Grand Valley installed some wells to look at the groundwater. So we're going to kind of examine groundwater, kind of compare it to the surface water in Sand Creek. And so first, if we just kind of look at some water samples, you can see there's quite a difference in color. We have the water sample from Sand Creek here to the right, and you can see that it's much more turbid and much darker color. The groundwater sample from a well is much clearer. So that would be one particular question to kind of consider. So particularly during high discharge events, there's a lot of turbulence. So our surface water from Sand Creek is able to keep fine particles in suspension. And in contrast, our groundwater travels much more slowly through the surface. And here we have groundwater moving through pores and probably mostly sand. And so because it's moving so slowly and there's not really an opportunity for fine-grained sediment to be kind of carried along with it. In addition, our groundwater is moving through pores, and fine-grained sediment just doesn't travel through pores that easily. So groundwater, on the other, typically looks pretty kind of clean in contrast to surface water, especially after a storm event when we have high velocity, high discharge conditions. So that's kind of the first observation to make. Another observation we can kind of make is with temperature. So the water temperature of this sample here is 10.5 degrees centigrade. So 10.5 degrees centigrade. And our groundwater sample, when I collected that, do you think that the groundwater sample would be higher temperature or lower temperature? Well, the groundwater sample is at a temperature of about 7.1 degrees centigrade, so almost 3 degrees colder centigrade. And think about that for a second. So much of this water from the creek that we're looking at fell as rain probably yesterday, and we've had warmer conditions. In contrast, the groundwater that we're looking at has been below the ground surface, hasn't been exposed to the sun, so we shouldn't be surprised that our water sample is relatively colder. In addition, we're here May 1st, so just a couple of months ago or so, we had cold conditions, and so any water that infiltrated into subsurface, 3 or 4 months ago was pretty cold water. So that's another thing, the difference between the temperature of our warmer surface water and our colder groundwater. As we monitor the temperature of the creek over the summer, we can use temperature to help us explain perhaps how much water is going into our stream from groundwater. If the stream water is relatively cool on a very hot day, you might suspect that some of that stream water, a lot of that stream water might be from groundwater discharging with this cold temperature. Okay, so we see that this visually has a higher turbidity than our groundwater. What we can also do is do another measurement. We can measure what's called the conductivity of the water. And the conductivity of the water is a measurement of how many dissolved ions there are. So this represents ions dissolved in the water. You can't really look at the water and tell if it has a high or low conductivity. You have to use kind of a measurement. So let me show, here we have a conductivity probe. And conductivity probes are relatively inexpensive, and they're just a valuable tool for doing water research. And the way a conductivity probe kind of works is it has two kind of electrodes that you can see here. This one does more than conductivity. Those two electrodes, when you put them in the water, it measures how easily electricity travels through the water. And if you have a lot of stuff dissolved in the water, then you have a higher conductivity reading. So here For the stream, we have a conductivity reading of about 332. And so that isn't like concentration or anything. It's a relative measurement of how many ions there are. Okay, so 332. And now you can see here we have very clear water. Let's see what we have kind of for our groundwater sample. So our groundwater sample, as you can see, has a much higher conductivity of maybe around 680 or so. So almost twice as high a conductivity. So again, conductivity represents the dissolved ions. You just can't look and see whether it has a high conductivity or not. You have to actually measure it. So now let's think about, well, why would groundwater have a lot dissolved in it? And what sort of things might influence the conductivity of our surface water from Sand Creek? So groundwater, essentially traveling through subsurface materials, there's a good chance that things get dissolved in water. And because the groundwater has been in contact with materials, there's every opportunity for things to get dissolved into groundwater. So we shouldn't be surprised that groundwater tends to have a higher conductivity. In contrast, rain, when water falls as rain, it typically has a very low conductivity. The process of evaporation doesn't actually bring any ions up with it. So rain has a very low conductivity, maybe like 15 or 10. So here in our surface water sample, especially after a big rain like we had yesterday and the day before, we're looking at a mixture of probably rain with a low conductivity and groundwater. So I believe that Sand Creek is still what we call a gaining stream. So groundwater with a high conductivity is still discharging into Sand Creek. At the same time, we have lots of surface water runoff from all the rain that is also entering Sand Creek. So that low conductivity rain is mixing with the high conductivity groundwater to give us kind of an intermediate conductivity, is part of the story to kind of share. So let me show you kind of some sampling for groundwater, some of the tools that we use to kind of take samples. And so the first thing I want to kind of mention is that geology, most people, when they think of geologists, they don't think about people that deal with water. But I actually studied groundwater for 5 years. So geologists also are interested in kind of groundwater. So this is what's called a bailer. This is what we're going to kind of use to collect a water sample. It's just a clear tube, and it has a little check valve here at the bottom. So as you lower this down, the check valve gets pushed open, and as you pull it up, the check valve will close and hopefully give us a sample. So you kind of lower the bailer down to get a sample of water, and kind of pull that sample up. So we have water filling our bailer here, and it's not as clean as the sample I showed you, but it's relatively clean. These wells haven't been developed or maintained a whole lot. So this is kind of our groundwater sample. So we can get a sample from that. This here, so we can use wells for water quality to collect a sample and analyze the well. We're also interested not just in the groundwater quality, but we're interested in what direction groundwater might be flowing or traveling. And so what this tool here, this water level indicator, will enable us to measure the depth to water in our well. So this well is only about 5 feet deep, and we're going to use this probe to kind of measure the depth to water. And the way this probe works is it's kind of calibrated so that it buzzes when it hits the top of the water table. So we'll kind of lower it down, and it'll buzz when it hits the water. And then we can kind of measure the depth to water pretty accurately by measuring on the tape kind of where that buzz first starts. So here we can see that the depth to water was 2.75 feet beneath the top over here, 2.75 feet. And since we took water out of the well, we should expect that depth to water to kind of change as the water level kind of recovers. So that's something else you can kind of do with a well also. So the reason why when you're pumping water out of a well, water continues to flow to that well is because when you lower the water level in the well, that's the lowest water level in the area, so groundwater from your aquifer is going to travel into the well. So I removed some water, so since I stopped removing water, water's flowing into that well until it kind of reaches the equilibration point that it did initially. And the amount of time it takes for that stability to reestablish depends on how permeable the aquifer material is. So if you have a sand and gravel aquifer, that recovery is going to happen very quickly because sand and gravel is very permeable, water will flow right in it. If you have not too much sand and gravel, if it's more fine-grained material, it might take hours for that water level to kind of recover because water isn't flowing as readily through that. So even something as simple as kind of monitoring the recovery of the water level in the well provides kind of some qualitative information on what the aquifer is. Of course, when this well was installed, they should have kind of logged the well and described the different sediments that were being intercepted. So that's a little bit of an intro. The one other thing that we did was, it goes along with the water level measurement, was I measured 2.6 feet down from the top of the well casing. And what we really want to know is what is the water elevation of the water table and what is the water level elevation of the stream. So we did a rough estimate of that, and what we found was that the water elevation of the well here was higher than the water level of the stream. And what that tells us is that groundwater being at a higher water level at the water table here, groundwater must be discharging into our lower water level elevation stream. And that's called kind of a gaining stream. And that's normally what we have in Michigan. Normally streams receive water from groundwater pretty much all the time. The one time when that might not happen is a day like today. Potentially, if we had a well closer to the stream, we could see whether the water table continues to be above the stream or not. If the stream floods high enough, if the stream flooded really high, for some period of time, the water level in the stream could actually be higher than our water table. And if that was the case, we'd have a losing stream, and we'd actually have river water discharging into our aquifer for some kind of short period of time until things kind of go back to normal and we have a gaining stream. Okay.